Aldehydes and ketones are biologically important molecules that are essential to the function of the human body and to human health. In this video, we are going to describe so-called reduction reactions of aldehydes and ketones. This video is the companion to the last video, video 344, where we talked about oxidation reactions of aldehydes. Reduction is the opposite reaction. So let's go ahead and take a closer look at reduction reactions. In general, when we refer to reduction reactions, what we are describing are reactions where we decrease the number of bonds between carbon and an electronegative atom, such as oxygen in the case of reducing aldehydes and ketones, and as a consequence of that, to maintain a complete octet, we increase the number of bonds between carbon and hydrogen. And so what is going to be required in reduction reactions is a hydrogen donor, so that we are able to replace a bond or bonds between carbon and oxygen with bonds between carbon and hydrogen. And so with regard to aldehydes and ketones, the general reaction that we explore when talking about reduction is that aldehydes, where we have a hydrogen directly bonded to the carbonyl, as our group here, could represent a carbon atom or carbon chain, or it could alternatively represent a hydrogen atom in the case of formaldehyde. If we reduce this by treating with a so-called reducing agent, what will happen is that the oxygen up here becomes bonded to a hydrogen to give an OH group, and we also, to keep the octet down here, this carbon bonds to a hydrogen as well. As a consequence of each of these two atoms, the oxygen and the carbon bonded to a hydrogen, we no longer need that pi bond there to have satisfied the octet rule. Hence, our product of this reaction, if we draw it out in the same format that we drew up top here, will correspond to new bonds between carbon and hydrogen. And we can show that in blue here, H here, and H here represent our new hydrogen atoms that we have brought into the molecule. And we would describe this as a reduction reaction because to start, we had two bonds between carbon and our electronegative atom oxygen. And at the end, we only have one covalent bond between carbon and oxygen. Hence, it corresponds to a reduction reaction. The other way that we can assess that this is a reduction reaction taking place is our number of bonds between carbon and hydrogen has increased because we have our carbonyl carbon right here in the starting material. It's only directly bonded to one hydrogen. And then by the final product, that same carbon atom is now bonded to two hydrogens, corresponding to a reduction process. Analogously, if we begin with a ketone starting material, a ketone by definition must have each of the two R groups represented by one or more carbon atoms here of a carbon chain, a carbon ring, or whatever else. If we treat a ketone with a reducing agent, we will analogously see that the carbonyl group is converted into an alcohol group, much like it was up top with our aldehyde starting material. So here in the bottom with our ketone, when we reduce that, the oxygen atom here is going to form a bond to a hydrogen. Likewise, the carbonyl carbon also forms a bond to a hydrogen atom. And therefore, the product of this reaction would still have our two R groups. There are two carbon chains. And at the central carbon here that was originally the ketone group, we still have that oxygen present, but now the oxygen is directly bonded to a hydrogen, as is what was originally the carbonyl carbon is now also bonded to a hydrogen atom. And so what we could describe this as is that we have reduced a ketone, when we treat it with a reducing agent, to a secondary alcohol. We call this a secondary alcohol because our carbon atom that has the alcohol group on it is directly bonded to two other carbon atoms here and here because our R groups in ketones must be carbon atoms. In contrast, when we reduced an aldehyde molecule in our top example, what we found was that the aldehyde was reduced to a primary alcohol. It is a primary alcohol because, as we evaluated structure, our carbon that's part of the alcohol group, that's the carbon right here, is directly bonded to just one other carbon atom, making it a primary alcohol. And so as a general rule, when we reduce an aldehyde, the product of reducing an aldehyde will always be a primary alcohol. In contrast, the product of reducing a ketone will always be a secondary alcohol. So we can remember this as general rules where if we start with a ketone functional group, we reduce it, we create a secondary alcohol. Aldehydes get reduced to primary alcohols. Now, we've talked so far generally about reducing agents. That is, reagents that we can bring into the chemical reaction mixture that will allow us to convert the carbonyl group of an aldehyde or ketone into an alcohol group of a primary alcohol or a secondary alcohol. What can we use as our specific reducing agents? There are a variety of reducing agents available. And the reducing agents that we could use in a chemical lab would include hydrogen, H2, with a metal catalyst. We previously talked about using H2 with a metal catalyst in the case of adding hydrogen to alkene groups to create alkanes during, for example, hydrogenation of oils. Similarly here, the H2 will add across the pi bond to create the alcohol product. So if we were to react the aldehyde with H2 as our reducing agent, what happens is one of the two hydrogens bonds to the oxygen, here with my laser pointer, the other hydrogen of H2 bonds to this carbon to ultimately give this product where the two hydrogen atoms of H2 are what we show in blue in our product here. Analogously, the same would be the case if we were reacting H2 with a ketone to give this alcohol product here. So H2 in metal is a very suitable reactant for carrying out these types of processes. Additionally, in the chemistry lab, a substance called sodium borohydride, NaBH4, and I will write out the name for this as sodium borohydride, is another example of a reducing agent. In the case of sodium borohydride, what happens is that the hydrogen atoms here are donated to the reaction. In other words, these hydrogen atoms provide the source for reducing the carbonyl group to a hydroxy group here. Of those four hydrogen atoms, if you were reducing one aldehyde molecule, you use just two of those four hydrogen atoms. One of those hydrogens goes here, one of those goes here. And so, in other words, to put this a different way, with sodium borohydride, if you were balancing a chemical equation, you can actually reduce 2 units of ketone for each unit of sodium borohydride, because the sodium borohydride has 4 hydrides or hydrogens available to donate to the reaction. Finally, as our last example of a reducing agent, this one is our biological example. In reactions that involve reduction in biological systems, which are very common since aldehyde and ketone groups are common in biology, a typical substance that is used to facilitate reduction is referred to as NADH, or spelled out, nicotinamide adenine dinucleotide. And I will write that out since that is a bit of a word jumble there. Nicotinamide with the N and NADH, adenine for the A, dinucleotide with the D. Where does the H come from? The H refers to a hydrogen atom that is bonded to this molecule and donated during reduction reactions. So this H here refers to a hydrogen that is donated from NAD to the organic molecule during reduction reactions in biological systems. And NAD and NADH are very, very common across biology. They are essential to the function of the human body as well as to a variety of types of cells. And the H here is the hydrogen that's donated in reduction reactions. So let's take a little bit of a closer look at NADH here as a biological reducing agent and talk about how that process happens. In this image, we see abbreviated structures of the molecule called NAD plus on the left. We call it NAD plus because there's a positive formal charge on the nitrogen atom right there. And then as well on the right, we have the substance that we refer to as NADH, where H is the hydrogen that is donated in order to reduce organic molecules, such as the carbonyl groups of aldehydes and ketones, into alcohol functional group products. looking at the structure of NADH, nicotinamide, adenine dinucleotide on the right, we see some abbreviations here. ADP stands for adenosine diphosphate. This stands for ribose. These are building blocks of DNA. NADH here plays a different role than a role in making DNA. Instead, it is used in reduction reactions. So NADH, the specific H that is referred to here, is one of these two H's down here bonded to this carbon atom. We'll highlight that one. You will notice that as you go from this side to this side of this reversible reaction, that as we do so, we go from over here having 2 hydrogen atoms in NADH to here having just 1 hydrogen atom in NAD+. And so what happens here is that this hydrogen atom is donated to an organic molecule such as an aldehyde or ketone in order to reduce it. This process is facilitated by enzymes, which act to greatly enhance the rate at which reactions of oxidation and reduction take place. So in the case of a typical type of reaction that you would see biologically, if we had a representative aldehyde or ketone, I will abbreviate this like so as a aldehyde molecule, and I'll define R as a carbon atom here. What we would find is that we would have an enzyme to carry out this reaction as the catalyst, and NADH as what we would refer to as a cofactor for the enzyme, an essential organic molecule that binds to the enzyme and confers upon the enzyme specific qualities and characteristics that the enzyme needs to function. In this case, the NADH is essential because it provides the hydrogen atom that is donated to the organic molecule during the reaction. So during the reaction that the enzyme is catalyzing a reduction reaction, what will happen is that this hydrogen atom is donated to the aldehyde molecule. And in actuality, it can be a couple of these being donated to the aldehyde molecule, so that ultimately we replace this carbonyl group of our aldehyde with instead a hydroxy group of an alcohol. So I'm redrawing the original skeleton of the aldehyde, but now rather than having an aldehyde group, instead we bond a hydrogen here and a hydrogen here, and it's this hydrogen atom right here, which I just highlighted and I'm laser pointing, donated by the NADH. So NADH is a biological reducing agent because it donates that hydrogen that's necessary for taking a carbonyl group and converting it into a hydroxy group. This is essential to biochemistry because enzymes, in many cases, carry out oxidation and reduction reactions. In the case of enzymes carrying out reduction reactions, NADH is commonly the source of the hydrogen that is used to reduce organic molecules.